All right, so we're still waiting to get my mic here, so we're getting started as soon as I get my mic system back in operation. And I need to make sure that also it looks good. So it's gonna be like here, and then like here. Now let me see how it appears in YouTube. Hey, before we get started, so before Mustafa is here, I want to show off a little bit. You know, the interview was 2 weeks back on Tuesday, and that when the Greg was giving your lecture, and eventually I changed my presentation completely. Altogether it was a different presentation that I practiced with you guys, and the slides that I used in my presentation, they were eventually like. Let me show it to you. They were like this. Oh, Mustafa is here. So these were okay. So you cannot see it yet, but I'm gonna put this on. Oh, thanks. Thank you so much. Yeah, thanks. And one more time, I'm sorry about that.
That's fine. Let's just check the camera position.
Sure. I need to put this one on, and then the quality should be fantastic.
Where have you attached the? Yes, this.
Yeah, it is. Yeah, it is. But
Because I just wanted to check that location of the green screen.
green screen.
Because
Yeah, sure. I'm gonna.
you can see it.
Because what is missing still is a video capture device. I think I don't want to use this one. Yep. So we need to
Your
move.
settings are still off.
My settings are. Yeah, I know it is off. I know it's off. But I need to stand here, roughly here. And we need to move this a little bit. Is this blocking a view right now?
Exactly. We have to.
Okay, so let's move with this side. Like here. I'm gonna put my gears here, this end. Okay, that's the max. That's the max we can go. But you need to change the camera too. How did you like about these AI workshops? So they were okay. So quite what? So it wasn't easy subject. Yeah. Yeah, I'm sure it wasn't easy at all. So let me just see that. How can I put this?
The green screen location is still not good.
Still not good.
So if you could just attach this so we can see that where the projector projects the screen. So I
Hold
can
on.
move the
So
green
hold on.
screen.
So if it's gonna be like this.
No, like if we know that how much it occupies, like we can move it a little.
Yeah,
bit.
but it can be like, so you're pointing, kind of. It should be pointing me right now. Change the camera to this direction. Bit more. So it's so funny that it comes with a pretty delayed echo. It's like this. Is this now kind of middle? But still is not. Oh yeah, I know why. I know. Because I cropped that incorrectly. So I can make this looking better. Here.
Yep.
That's the way to go. No. Only thing left is that I need to put this background, this chroma key.
Also, you can crop it from the height. Like,
Oh, okay.
I know that you're tall.
I'm tall. I am tall. So you said that I'm not that tall?
No, you're tall, but you know.
Okay, what should I, so how should I filters here? What was the name of this filter? Because it seems that there's no chroma key here. Effect filters. Background removal.
The only thing which I remember was the chroma key.
Chroma key. But it's not here. Oh yeah, I think it is here. Chroma key. Yep, that's good. That's really good. So I'm gonna just crop these a little bit here.
From the height, yes. Yep.
And here too.
A little. Yes, it's
Like this much. Okay.
Yep.
Okay, guys. So we all set. So I said that I wanted to show you, before we getting started, I wanted to show you how were my slides during this interview. And the interview slides were like this. Okay. All right, so Mustafa, I think we're good. So it look,
Yeah.
yeah, but I'm gonna,
But
it's
can you project it?
I figured I can. Just a second.
And also try the full screen because I'm not sure that whether you're sharing the whole screen or just the
So now it should be okay, isn't it?
No.
No, can you show me that, how it appears? Like still like that?
Yes, because I think that you're just sharing the PowerPoint thing. You have to share your whole screen.
So let me share this one. Okay, so it's gonna be fine now.
Yep, nice one.
Good thing. All right, so these were my slides. What happened was that, I got
So when do you think that you...
I gotta be 15 to noon.
Okay.
15 to noon, I'm gonna be ready. Okay, guys, so long time no see, first of all. So it been period number 3 that we met the last time, because the first lecture in this period was delivered by Arjen Schwab. That was this bicycle story. And then what came after that was this AI workshop. I hope that you enjoyed, because the AI workshop is something that is important. It is important. It's good to be aware that AI is more than a ChatGPT. So that, I think, was the purpose of the workshop. I mean, ChatGPT and the large language models too are important, but there is so much more other than that makes an impact to engineering. So that was all delivered by Greg. I hope that you enjoyed. And before I moved out, or I stepped down, I practiced this presentation that was in my ERC interview. And eventually the slide that I was used was like this one. This was my opening slide, and then the problem was like this. So it was completely different than in the previous cases. So you see that this is no longer made by me, but graphical designers. You can tell that from, just basically how it looks. This looks great, and mine wasn't that great, and now it's clear. So we have a problem, fatigue in the welded joints, and this is a pretty severe problem because in a welding process there is these defects and high residual stresses that makes fatigue, welded joints to suffer from fatigue failures. This is a big problem, and it's going to be even bigger because there's a high trend to use high-strength steel to make structures to be more lighter. And then we don't have any proper way to measure the fatigue life at the moment. But this project will introduce this. And because we don't have a proper measures, we have dangerous and costly failures. How it's going to be solved will be based on this. So it's going to be based on flexible multi-body dynamics, and there's a fatigue life prediction. This I modified already, so there is a sensor here that shows how much the fatigue life is left. And the technique behind was this floating frame reference formulation that you guys are now familiar with, sub-modeling technique which you are not familiar with, model order reduction that you are familiar with. So how to make models to have a less degrees of freedom based on this model reduction. Alarm fluid theory is something we discussed previous semester, and then these environment models we haven't discussed.
but we're going to touch them shortly today if we have a time. And then these are the objectives and then the outcomes. And my last slide was this, 5 minutes. So way much better than it was. Yeah, visually, so much better than it was. And I think no videos anymore because I got the instructions that, if you want to use the videos in these 5 minutes, makes people just confused. So better not to use it. Better not to use it. All right, so that was my story. And then the next story that I wanted to tell you is this. Oh, you don't see this. Well, let me put this visual. All right, so now things are going to be not optimal because I want to take you back where the time that I was stepped down. And just before I left, we discussed about modal order techniques and how to select the modes. I want to discuss about a couple more matters in that regard. And then once done with that, I want to just short like a news flash. What is something that is called mass invariance, which is a big part of the floating frame reference formulation. And then we're going to move on. And what we're going to move on, and once we're going to move on, we're going to discuss about conduct modeling. Altogether different subject matter, but I think it is something that is good to be aware of. And then what happens after that is this. There's going to be one more lecture that is not going to be part of the written exam. It's not going to be part of the exam, but I really would like you to hear this. This is like what makes a difference in your career? What are the skills? It's basically your presentation skills, something that is a very, very important if you wanted to be successful. How you can develop your presentation skills to make to be something that others can understand. And this lecture is not going to be delivered by me, but it's going to be delivered by Dr. Scott Semken. He's American guy, so his English is pretty good, so it's very much understandable. But I think the presentation is something that you can make a great use in your career. That's why I would like you to hear it. And if you feel that, actually, I don't care, I don't want to learn anything about the presentation skills because my presentation skills are already so fantastic, fine, don't come. Don't bother to follow this. But I highly recommend you to follow this. Highly recommend. By the way, what happened? Like, why there's only such a few people in a lecture room? Are they all lost or they lost an interest?
I think AI was a little bit overwhelming.
So it was too much to deal with.
I guess, and a bit of confusion also. Somebody was waiting also for Greg, I think.
Here, I mean, in online?
Yeah, in the Teams. So now they switched to YouTube.
Okay. Okay, so it wasn't clearly informed. Yeah, I thought there's going to be one more AI workshop.
Or everybody thought we're not seeing you anymore.
No, yeah. Okay, so here's the plan. So it's going to be next week that Scott is here, and then it's going to be one more lecture that is delivered by me. Okay, the next week is not mandatory. Skip it if you're busy, seriously. But I would like you to learn it because the difference that I have seen between the international students and Finnish students, which I hate even to discuss about this, that they are different teams because we only have one culture, one religion, one nation. And one nation, religion and culture is LUT culture. But still I see that every now and then there's, people are saying international students or, Finnish students and discussion like that. All right, so if you look at closely, like if there's any difference between these different groups, they may be. And, that maybe the difference is that the presentation skills. And that's why I would like others. I mean, that it doesn't hurt if you have a good presentation skills. It doesn't hurt if you're going to make yourself stronger in this regard. And please follow whatever Scott wanted to introduce you next week. And then I will be back on week 16, which is all others, and including the questions for next midterm exam. I know that there's also a lot of confusion about midterm exam. And there was a lot of email correspondence back and forth between you guys and Mustafa and Suraj and me and so on and so forth. I hope that is all settled now. I hope so. Keep in mind that the exam is not that major part of the course. And the next one is just going to be very limited number of questions available. because we only covered the bicycle dynamics. Today we discuss about these final matters about modal reduction, and then I really would like to spend a little bit of time about what else we can do with the simulation models. And one of the things that I would like you to be aware of is that how we can make a use of this technology for fatigue life prediction. We might even have a time to cover that topic today, but we'll see. We'll see how it's going to go. Okay, any questions, comments about the practical matters, the practicalities? How things appears? Is it okay? Quite okay. Okay. Let me think, what else? Yeah, another thing, this is coming to be a little bit late, but I don't know what your summer plans are. Are you guys, you were able to find a summer position or not yet?
Back to old job.
Okay, so you're gonna go back to where you left from?
Yeah,
Okay,
but maybe not exactly doing multi-body dynamics.
yeah, sure, but it's something, is it related to mechanical engineering or is it
Yeah, engineering, but
engineering?
like static fields.
Okay, good thing, good thing.
Is it typical to make a summer jump in Finland?
Yes, it is common. It is common. It is common, but you need to be the one that is actively looking for these summer positions, and it becomes to be a little late for that. They are alternative for what to do during the summer, because you are now a first year student, but soon second year student. So another possibility is that if you find nothing else to do, no summer position, then I recommend you to start doing your master thesis project. And the master thesis project is something that is a little confusing because sometimes you might get the financial compensation when doing your master thesis project. I know that if you're coming from any other country from Europe or worldwide, you have not heard this before. But in Finland is often the case that when you do your master thesis project, you will get the financial support. Not necessarily from university, but particularly if you do your thesis to help companies to do things better, then it's not unusual that you will be paid. Universities, that's a little bit of a different story. But again, there may be thesis topics available in the professors in the mechanical engineering, so it makes sense to go and ask, like if there's anything available this time. And even if not, that's okay, because if you're gonna get started this time, your thesis project, you're gonna finish that, I guess that you're gonna still able to finish that before the Christmas. So it only takes, 3 semesters in the summer to finalize your master degree. So that's one opportunity one option to consider. All right, but anyways, yeah, like I said, this is not optimal thing because when Arend was visiting, he delivered the lecture that was in a week 10, and I was have to move to this week, which is week 14, and now I know that you don't remember much about modal reduction and modes and stuff like that, but still I want to take you back to what we discussed in a period number 3. A short observations in that regard. And then we're going to discuss about the contact modeling. So that's my plan today. And if any time left, I want to take you all the way to how you can make a use of flexible multibody dynamics and how you can predict the fatigue life using flexible multibody dynamics. Okay, any complaints? So I heard that the instructions were not clear regarding the AI workshop and lectures, but anything else? Any other worries? Not much. Okay, all right. Anyways, I'm going to do a little bit of marketing for Scott's lecture because, of course, you can follow the Scott's lecture online like every single lecture here, but maybe it would make sense to come here to discuss with Scott because he's a pleasant guy, he's a really nice guy. And, of course, the online participants are limited in terms of interaction. All right. Remember when we discussed about this whole business about how you can use a finite element modeling as a part of the multibody dynamics? This was something that the idea was such, let me put it in the writing here, that you do your multibody model, and then you're going to take your finite element model, And your finite element model, which is, let me write it like, I think it would be better to write it like this. This is a stiffness matrix, this is a nodal displacement, this is externally applied forces. So what you can do here is that you can move from nodal space to the modal space. And the modal space, what relates these two matters is assumed deformation modes. Would you assuming that structure will deform as an entire structure? And this you can represent by using matrix that is coming from the shape of the structural deformation. These are the modes. Now modes multiplied by the modal coordinates, which is like the amplification associated for each one of these modes, is going to give you the estimation of nodal displacement. And the beauty of the trick that we can use in the model reduction is that this one here, which is typically consisting of very large number of components, I'm saying easily hundreds and thousands or millions, can be reduced to something that is tens, sometimes even less than a 10. Of course, you lose something. This is a trade-off. This is a deal like what is very much in a fashion today. Here in this deal, what you're going to lose is an accuracy, but you're going to gain is a computational efficiency. And this is, you must do this, because otherwise if you have this full finite element model, the computation would be so slow that it takes forever to figure out how the structure behaves. So how much you can lose computational accuracy? This is something that is not easy to say, and of course case dependent. It depends how well you can select these modes. Okay, so we learned that you can create the modes using eigenvalue problem. This is a very standard way to go and figure them out. But eigenvalue is not very general. Sometimes you want to use something that doesn't need that much of the skills from the operators, users. And one of the methods that is heavily used is something that is called Craig-Pompton model reduction method. It comes with a certain problem, so it's not optimal way to select the modes. So it's being demonstrated in the literature. In some cases, it's suffering quite a bit. But generally speaking, is a method that is works pretty well. And the beauty of the method is that it doesn't need that much of a thinking. Doesn't need that much of a thinking. And it fits to multiple, wide variety of problems, again, without serious amount of thinking. How that works, how this Craig-Pompton works. It works in a way that you just only need to, what you need to do as a user is that you need to be able to select the points of interest, and the rest will be automated. Points of interest is something that in your structure could be the places where the joints are located in your flexible body. Like in this kind of this is a cantilever beam, even though that is a plate structure. This point is connected to crown, so there's a joint. This point is also connected to crown as there's a joint. There may be another point of interest, like possibly where there's a pin force, or let's say that there's a force that you really wanted to closely look how much this particular force is introducing the strains and stresses. It could be located like here. And this is it. You do this selection, what you can call like a point of interest. Here, of course, we want to use a terminology that is more along the engineering. And terminology here is a boundary degrees of freedom, which are the point of interest. Okay, so once you do this point of interest, that's it. And then you just say the software, okay, I made my selection for point of interest, you do me the rest. So what happens when you say that, okay, you do me the rest, is that the software is actually categorizing your degrees of freedom of the entire structure to two different categories. The one that is boundary degrees of freedom, again, the one that is this point of interest, and rest. And the rest, this time is called like interior degrees of freedom. Rest. So this one is, when you look at the number-wise or unit-wise, the interior degrees of freedom is significantly bigger, way much bigger than this boundary degrees of freedom. Significantly better. All right. Now, what happens under the hood is that finite element software, which is typically the software to do this computation, reorganize your mass and stiffness matrix such the way that this boundary degrees of freedom will be relocated in the upper left corner of your mass matrix and stiffness matrix. Interior degrees of freedom will be located in the lower left corner of your mass and stiffness matrix correspondingly. Okay, once you do this, then you're going to start selecting, or you're going to start computing the two different sets of deformation modes. And these two different sets are, first of all, something that is called normal modes. So you're going to take only these interior degrees of freedom, forget about the rest. Only the interior degrees of freedom from the previous here and here. And then you're comparing the modes associated with those submatrices, two submatrices, which is a mass and the stiffness. Okay, so that's going to be your first set of modes, and they're going to look like this. Momentarily, we're going to visualize how they look like. And then you're going to compute something that is called static correction modes or static modes. And in the static modes, you're going to forget about mass and acceleration, but you only take a stiffness, and then you're going to compute, you're going to solve this one out of this previous equation. This is going to give you another set of modes. So now you're going to get two different kind of the modes. The one that is called static modes, another one is called normal modes. All right, how they look is this. Here is a beam structure. In a beam structure, I'm saying, okay, point of interest. Boundary modes are the one that is located in this end, and in this end, and in the middle. Those are my points of interest. And the way I'm going to do the computing is that I'm going to first attach these nodes rigidly to ground. And then I'm conducting my eigenvalue analysis for rest of the degrees of freedom. So they're going to behave like this. Or, then it's going to be more and more complicated depending how many modes in this category you want to select. And then there's a static correction mode, which again, I have these beam, 3 points of interest. So I'm going to attach these points of interest to the ground, but I'm releasing 1 degree of freedom at the time, and I'm introducing the unit displacement to this 1 degree of freedom at the time. So, like for example, this one here, the unit displacement will be y direction, x direction, and the rotation. And this is going to give me something that is called static correction modes. And this is another set of modes. This is more like very much interested in these local points here, whereas the other one is more global behavior. And now this combination is something that is that people have figured out that is a really optimal way to model most of the structures. And the only thing, again, so I want to repeat it, the only thing needed is that you only just need to tell the software what's the point of interest. Rest will happen automatically. Okay, so now you're going to get these fixed interface normal modes and static modes, and that's it. This is where you could stop this. You could stop computing, but most of the software, they want to make one step forward. And one step forward is something that you want to get rid of the one minor drawback associated to this method. And the minor drawback is the fact that the static correction modes are not orthogonal. They are not orthogonal simply because they are based on static displacement. Others are based on eigenvalue problem. An eigenvalue gives you the modes that are always orthogonal. I don't know if you remember this, but orthogonality brings one fantastic feature along with the orthogonalization. And the feature is that when you're multiplying the matrices, stiffness, and mass using orthonormalized, the matrix that is orthogonal, you can only get the diagonal representation. This is one thing that helps the computing in the future. And some people prefer that everything you do must eventually be in orthogonal form. And this set of modes, static ones, is not. It's not, because it is based on displacement. But is this a serious problem? In my mind, it's not a serious problem, but many people feel that this is something that needs to be fixed. Okay, it can be fixed. And the way you can fix this is that you take your combination of modes, which is, again, static correction modes, and there's a fixed interface normal modes. You combine them in a one matrix. Then you compute the new mass and stiffness. And they will not be diagonal representation, but off diagonal. But the size is already reduced a lot, really a lot. But it's not that diagonal. But you can force, what's this? So was this like a timer? Is there some kind of switch there? Oh, it's coming back. Is it that you guys need to move a little bit? Otherwise, it's going to take the lights off. Right. So I was about to say that you just take these matrices, these computed modes, an original mass and a stiffness, and you recompute revised mass and a stiffness. Okay, so they are not orthogonal. So the last thing that you can do is that you can take these revised mass and stiffness and conduct the eigenvalue analysis for those matrices. This time, much less degrees of freedom comparing the original problem. Significantly less degrees of freedom. Okay, so the eigenvalue analysis goes like this. So you take these, this guy you're going to put here, this guy you're going to put here, and this is how the vector, your final solution look like. And now when you compute using this matrix and you compute this and this matrices, you're going to get orthogonal representation. And then the purity problem is fixed. But it's only the purity problem. I don't see that as a very big problem, but it's a little bit of like purity problem. Okay, so the procedure in total is like this. You take your ANSYS or any final assembly software you want. You compute fixed interface normal modes, static correction modes, and then you're using this, forcing them to be orthogonal. They call this, as a name wants, orthonormalization. When you're forcing them, particularly this guy, to be orthogonal. As a consequence of this, you get modes that are quite much about the free modes, as something that you can have a close look about point of interest, these boundary modes. Okay, and then you can go to your multi-body model, and you can do the computing. That's how it works. All right, Craig-Mountain method is often used approach because it allows to describe the local deformation due to the forces and joints. It can be used for beam-like structures. It can be used for plate-like structures. It allows to describe structural damage. Okay, each one of them is correct, but the one is a real reason to use it. Each one of these are technically correct statements, but the one only is technically, the one that is a real reason to make a use of the Craig-Mountain mode. Oh, yeah. So it's a pretty sensitive thing. Okay, so the Socrative is on. So can you guys take a look? Oh, it's a look too. So it's not really. It should be open. Let me think, why not? Okay. Sorry, guys. Sorry, I was in the wrong room. Finish activity. Launch. Okay, so it should be on. No. Still not. So I need to launch this. Finish activity. Launch this. Okay. And the room is LUT2, correct. So it's LUT2. So can you see? Oh yeah, you don't see anything at all. Okay, so is it on?
Yeah.
Okay, and you guys. Good thing. Okay, so let me, I'm gonna get back to this momentarily. So let me continue my story. And I'm gonna take these off here. Just a few observations and yeah, good thing. So it's gonna be like this. All right, so this floating frame reference formulation, you know, it is something that you can use pretty much any kind of the elements you want. Of course, there is a certain limitations like symmetry elements or something like that is not allowed to use because you need to know the entire weight of the structure. So that's kind of the limitation. And but it says that, you know, most of the cases, the real use of this method is based on solid elements, not so much about plate elements and beam elements. Beam elements, for sure not, because the beam element structures are typically so simple that you can model them using techniques like lamp mass approaches. But solid elements becomes to be so complicated that these are hard to use any other element types than solid elements. Then, of course, you know, when you're computing these, when you make a use of the modes, what you need to do is that you need to take these rigid body modes out, because the rigid body is already described by body reference coordinate system. Remember, that's the deal, that's the thing that we did in the very beginning. So we said that body reference coordinate system is the one that takes care of the large reference translation and rotation. Now, if you have a rigid body modes included to your mode set, it's going to make things confused, because then you have rigid body modes described twice, and it's not going to be well operating system because it needs to be described only once. So because the reference coordinate systems already take care of the rigid body motion, you don't need this anymore. And then, you know, typically when you have finite element model, you can use as-it-is. No need to make any kind of special treatment before you can make a use of that in the multi-body system dynamics. Take the model pretty much as it is, and then you're good to go. But like I mentioned earlier, if you have a symmetric models, which is not that much used at the moment at all, but when I was younger, so it was quite much used because of the computational efficiency reasons. This is something that you cannot use. All right, I have another question. In a floating frame reference formulation, rigid body modes need to be removed because rotations are assumed to be small. Deformation are assumed to be small. The reference coordinate system takes care of the rigid body motion. Or finally, damping is assumed to be insignificant. Okay, so let me take myself to the Socrative and change the question to be the next one. And then we're going to discuss something a little different. So this is my Socrative. So you want to take a look at how are the results. We still have 25 students, which is good. I thought that is less than that. Okay, the results are like this. Oh, the number is increasing. Look at that. 29. Okay, I'm going to close this. Nice. Nice, because it allows to describe local deformation due to the forces and joints. That's what it is. That's what it is. Next one, I think that the success rate is going to be even higher than this one. In the floating frame reference formulas, and rigid body modes need to be removed because rotations are assumed to be small, deformations are assumed to be small. Reference coordinate system takes care of the rigid body motion. Damping is assumed to be insignificant. Okay, and I'm going to leave you guys to think about this, and I'm going to give you the few hints about how you can work with these modes. Okay, this is Atom software, which we don't have an access in the university any longer. But once we, when we had this access, the Atom software was using this kind of like a modal selection based on the visualization. And the visualization is one of the most powerful tools even today to select the modes. So if the modes seems to make a sense, please select them, because the selection is based on your engineering skills. And if you feel that there's a possibility that the structure can deform in a certain way, keep them in. And if you feel that absolutely there's no way that that structure can deform this way, take them out. And this kind of visualization was like here you can see how it behaves, and that was like pretty much the only thing that you need to take care of. And these are the visualizations. So these are the structure of this 1 degrees of freedom crane. You see that this kind of deformation, for sure, they will contribute the final deformation of the structure. This kind of local deformation, probably not so much, and you can ignore them. So visual inspection is still the most powerful way to move forward, which is kind of unusual. There are, yes?
In this case, there are like horizontal deformations as well.
Yeah, so if,
Horizontal, can we have to keep track on them as well? Because it's like a crane, the force is only going in vertical direction.
right, so the crane is like a planar structure. Yeah. And you can get the modes that are spatial modes. And some of the modes that are perpendicular with respect to loading condition. I don't think that you can make a use of these modes because the deformation, if the force is in this direction, deformation should be in a line of this direction. So if they have like this direction, there's no forces in this transverse direction. So you can, with high level of certainty, you can ignore them. Okay, and then there is one more like automated way that you can select the modes. An automated way is quite nice. It is based on how is the strain energy associated to each one of the modes. Strain energy goes like this. Strain associated to finite segment model as a total can be computed like this. So it's going to be the integral. This is a nodal displacement. This is a stiffness matrix, and this is a node. Like this. This is how you can compute it. And now when we're using the fact that these nodal coordinates are related to modal coordinates like this, once we submit this information here, then we can compute how much is the total energy of the system. So this is something that is possible to compute. And then we can make a plot, like this is a total energy, let's call this as E. And then this is a mode ID. So we have here mode number 1, which is the ones we took these rigid body modes away. They are like the first deformation mode, mode number 2, so on and so forth. When you look at like how much each of these modes are contributing to strain energy, it typically looks like something like this. Like mode number 2, let's say that for some reason mode number 1 is this transverse direction, so it's not contributing much. The second one is contributing, like if you think about this, is 100% here, this is 80%. So it could be as high as 80%. And then there's could be modes here and there that contribute like 10%, 5%, and it only needs a few of them. And the rest will contribute less than 1%, way less than 1%. And this is a system that you can set there like a threshold value, that if the contribution is less, like here in this case, is a 0.0001, forget about it. Because think about it, how much it is contributing strain energy so insignificantly that it doesn't make much of a difference. And if it is less than that, forget about it. Forget them automatically. And this is the automated way to do the selection. I would still say that the superior way to do the selection is visual inspection. Because this one here comes with a little bit of problem because it only works when you have all the modes in and when you have a certain kind of work cycle. If you change the work cycle, you should compute the total energy again. And this is not so straightforward. So my instructions to you, trust your engineering sense rather than anything else. Okay, so this is an automated way to do the selection. All right, so verification for flexible bodies. Compare the inertia properties of flexible bodies in finite element model and in multi-body model. And this is why, because you can easily make a mistake about units. You might have a millimeters, other software, another software is a meters, and then they don't match any longer. Compare the natural frequencies of free modes, and those should be roughly same. They are not exactly same because of the auto-normalization process, but they shouldn't be much off either. Compare the deformation. This is a good way to verify too. All right, that's it. I'm gonna have another news flash, very brief about mass invariance. I'm not gonna use many of the slides because the story itself, mass invariance, is a massively complicated story. Okay, so it goes like this. Remember when we started from the rigid bodies, the kinematics was such that we have the vector R describing the body reference coordinate system. Then we have a rotation matrix, a vector U bar. And now what we did was that we changed the kinematics. Not significantly, but we added one extra component to kinematics, and it's a vector U bar F. Vector U bar F. Now, because the kinematics is being changed, so we need to redo everything. We need to rewrite the equation of motion. We have to write velocity, acceleration, virtual inertial forces, virtual external applied forces, virtual elastic forces. Everything needs to be redone. So even this minor change, which seemingly is not much, is still touching the kinematics. Kinematics is always something that you are not allowed to touch, or you are allowed to touch, but if you do so, you need to rewrite the whole story again. Now this is exactly what happened here. So you have the vector U bar F that is now changed. Now because of this, you have to somehow make sure that your finite element model, and your multi-body system dynamics is coupled. They need to be connected. Kinematics is the one way to take care of this, but in practice you can combine these in inertial forces or in elastic forces. And the floating frame reference formulation, you do the combination of these two procedures in inertial forces. And this is where the mass invariants are coming from. So what you do is that you take this kinematic, you rewrite the equation of motion. When you rewrite the equation of motion, actual combination of the finite element model and your multi-body system dynamics will take a place in your inertia forces. And now comes the mass invariance. Mass invariance is telling you how heavily finite element and multi-body system dynamics are coupled. This is kind of funny that the user can make a decision if they are fully coupled, partially coupled, or not coupled at all. If not coupled at all, you can run your flexible bodies such that it is actually a rigid body, which is, of course, makes sense in certain cases because then you can run things fast. Computation is super efficient. But of course, you want to make sure that eventually you run things as a flexible bodies. That's what you want it to do. Okay, so this combination of how well or not at all combined is defined by mass invariance. In mass invariance, story goes like this, that you first have to define what are the variables. Now we have more variables. Because in addition to reference coordinate system, which are the coordinates associated to these ones, we have these model coordinates. They too are unknowns. Because of this, eventually when I write my equation of motion, it's going to look altogether different than the one that are based on rigid bodies. And once I look at my mass matrix, the mass matrix is going to be very complicated. So it's going to be a big mess. And one of the components in the mass matrix is going to be this i's. I1 all the way to I9. And these are the ones that are called mass invariants. Okay, so here's the story. One more time. So you have these variables, which is a reference coordinate system and the model coordinates. You derive your equation of motion. You end up to have a mass matrix. In a mass matrix, you can compute a few components prior to simulation. And those components are called mass invariants. Now, the user, surprisingly enough, can select which one out of the many invariants are active during the simulation and which ones are inactive. What that means? It means that is it your finite sum model and multi-body dynamics completely decoupled, partly coupled, or fully coupled. So that's what they means for. And this is something that you need to be very, very careful, of course, because you can do everything correctly, but then the mass invariants are not active, meaning that your system is rigid, or partially coupled, meaning that you're not going to get correct solutions, but your computational efficiency is very good. So that's what the mass invariants are for. And they look like this. So they are very complicated. They have not clear names. This is a screenshot from the software. So you have this opportunity to select which one of the many you keep the active. My recommendation, keep them all active all the time, because that's what tells, make sure that they are fully coupled. That's why you do the flexible bodies anyways. It doesn't make much of a sense to do flexible bodies and then keep things loose. Okay, so that's mass invariance. So short story. So is it so what was the question again?
Is it embedded in the mass matrix or it's like separate?
Yeah, this is embedded in a mass matrix. So it's completely like inherent part of a mass matrix. But when you forget about them, it physically means that your combination to flexible bodies is not strong anymore, or it can be fully decoupled. That's what it means. So it's kind of weird that you have this opportunity, but that's where the mass invariants are for. So they tells you if you have fully coupled, partially coupled, or no coupling. All right, so that's what they are for. Okay, my 13th class quiz is this. Role of mass invariance. Allows to describe the structural damping, allows to describe externally applied forces, couples the stiffness and damping, couples the finite sum model and multi-body system dynamics. So what they do for. Okay, let me discard this. Let me take myself here. You still see me well? Okay. How is going to be success rate of this in the floating frame reference formulation question? I'm thinking it's going to be high. 95. I'm feeling the same. Okay, so it's still very good, not bad at all. So it's percentage is fantastic actually. Let's see how we're going to do here. Role of the mass invariance. So what they're doing for you. Very good. So I get the answers already. All right. So let me continue my story here. You notice that I'm a little bit in a hurry today, but let me continue my story here because I want to discuss about a completely different thing, which is a contact modeling. Contact modeling. All right. So contact modeling is something that is big deal in pretty much all the dynamics. You have to be able to describe, excuse me, you have to be able to describe what happened when there are two objects colliding, when there are two objects having the contact to each other. And we have actually two principal ways to make it happen. This is a game that is no longer fashion, but there's a car and there's some object that is hitting to the car. You see that the car is like the suspension is doing something here, and you see that these are the game engines. The game engines they're pretty good in the contact prediction, but not necessarily so good in contact events description itself. Right. Contact modeling comes with the two parts: contact prediction and contact events itself. In most of the cases, the hardest part is to use the contact prediction method, because there is so many opportunities, so many possibilities how the contact can take place. Not at all easy thing. What comes in a contact modeling event itself? So we have two possibilities. Roughly speaking, we have two possibilities. Then we have like varieties of both of them. So we can use smooth dynamics or non-smooth dynamics. So they are conceptually very different from each other. Most of the games, they're using, well, I'm not sure what the games are using. I think that they're using smooth dynamics, because it's so important to make sure that you can run things real time whatever you're playing the game. So the real time requirements is so dominating in the game. So I think they're using the smooth dynamics. The difference is significant. But again, first thing, you have to predict if there's a contact event. If yes, then you have to move to modeling the contact event. And the contact event, you can use smooth or non-smooth dynamics. All right, another very important observation is this. Okay, so this is what I just explained, the contact detection, so contact event prediction, if contact takes a place, and if it takes a place, how you can model the contact. All right, so I want to just jump a little bit ahead of the time, because I want to come back here. If you have everything as a flexible bodies, as a deformable bodies, then life will be easy, very easy. Because then you can just say that, okay, flexible bodies, they cannot penetrate. And it's simple like this. They cannot penetrate, and because they cannot penetrate, the deformation takes care of the contact modeling itself. That's going to be a very, very simple thing to do. Like in a gear mechanics, like you see the figure here, the gears you could possibly model as a flexible bodies. And what you need to do is that you need to say that the gears, they cannot penetrate. And that's it. End of the story. But games and multi-body system dynamics, we typically do not model structures by using flexible bodies, but rigid bodies. And then things becomes to be way more complicated. Now, like I say, we have two choices here. So we can use a smooth dynamics, which is something that, if we have a ball like here, and the ball is touching the ground, as soon as the ball comes here, so it's touching the ground, like there's no geometries are not penetrating at all. So we can use inequalities as a constraint. Some similar kind of thing we model the joints, saying that, okay, the bodies you can do whatever you want, but you have motion limitations based on the joints. We can introduce the motion limitation here too. And that's going to introduce you the non-smooth dynamics. Or alternatively, we can do this. So this is a ball, and this is a surface. And it happens like this, that they're penetrating. Of course, this is not happening in reality. But this is an indentation. They are penetrating this much. And now based on how much they're penetrating, I'm introducing the forces to push the ball away from the ground. This is a smooth dynamics. This one here, where we're introducing inequalities, similar way we're introducing constraints like joints, is a non-smooth dynamics. All right, so now you know. So that's the theory behind. But let's go back to where I started here. We have here the two things to do: the contact detection and contact event modeling. So those are the two alternatives. Or let's say the two things that you have to do. The first, the contact detection, and if yes, there is a contact, then the contact event itself. Contact detection, it's well established science. And in most cases, you use a different variety of something that is called bounding box method. The bounding box, I don't know if you have heard about this before, but that's what they use in games. Bounding box is something that you use a different level of different sizes of objectives, and you're comparing whether or not these objectives are possibly overlapping or not. Example is this. The terminal structure, the structure we looked a little while ago, you can make a very big box, like root level box, top of this device. This is the one that touches the container and lift this up. This is a very big box. And within this box, the structure is located at. Then there's another even bigger box located here. This bigger box is an enormous size of box. And this enormous size of box is something that the entire ship is within the box. All right, next thing you do, and then there's one more box, which is entire container is within the box. Then what you do is that you're comparing whether or not this box here is colliding with this box. If yes, then you need to move on to more detailed description. If no, that's it. You do no further access. And the same thing here. So you're comparing whether or not this device is colliding with this container. If yes, you move on to more detailed description. If no, that's it. Forget about the rest. And this is a kind of efficient and must-have a technique, because if you look at the drawing symbols can collide very high way of there's almost like infinite number of possibilities. And if you think that you can model that like if-then, it's going to be so many if-then that it makes no sense anymore. Think about rally game. You have a car, here's my car, and the car rally game goes in a road, and the road is like 10 kilometers in length. And now you say that there's a possibility that the car can collide to trees that are located within this road, which is 10 kilometers in length. Again, there's going to be so many if-then. And you're losing so much computational efficiency if you're comparing whether or not the front bumper can hit the tree that is located far off here. It cannot. It doesn't make much of a sense to do it because it's so far off. So forget about it. Don't even think that they can collide. But as soon as it becomes to be closer, then maybe yes. And this bounding box is the one that defines whether or not there's this possibility to collide. All right. And as you can imagine, what happens if there is a possibility, like if big boxes are penetrating, then you move on. You're moving on to something that is called branch level description. And the branch level, you see that there's a smaller boxes here. Smaller boxes, like part of these lifting devices within these smaller boxes. Now you look whether or not these smaller boxes are still colliding with this container. And if still yes, if it is still yes, then you're moving the leaf level, which is the drawing symbols. You look like if the drawing symbols are actually colliding. If they're penetrating, if yes, you need to push them aside, away from each other. And that's the prediction method. And of course, there's many different varieties in the bounding box method. And these varieties are pretty much how you put the boxes top of your structure. They could be axis aligned, object aligns, but the concept is still the same. Axis aligned bounding boxes, oriented bounding boxes. It's just basically how you put these structures within these bigger boxes. Anyways, how you should do this selection depends a little bit of your application. But the bounding box is the prediction method, contact prediction method. Makes sense? Any comments, questions? And this is how your games are operating. If you look at, I don't know if you guys are not playing games or you might. No comments. No comments. Okay, like I say, if you would have deformable models, life would be easy. But we don't. We don't. So we need to use two alternatives, penalty forces or something that is called cone complementary approach. Cone complementary approach sounds like a monster name-wise, but basically it's inequalities. Inequality, similar way that the joints, like there could be inequality saying that, okay, this ball can do whatever it wants, but it cannot penetrate to this surface. So it would be like x equal to 0 all the time. That's the inequality. This is a constraint, similar way than remember when we're using the revolute joint, it is a constraint. But this is an inequality constraint. So similar kind of approaches. And this is super powerful if you have a lot of objects that could possibly contact with each other. If you have just a few bodies that can contact each other, penalty forces is the way to go, better way to go. Where's the limit? Okay, this is hard to say, but as a rule of thumb, tens of bodies, particles, use this one, hundreds or more, maybe better use this one. This goes all the way to tens of millions, even more. So this is something that there's a super efficient techniques available. All right, penalty forces is like this. Like I say, it's very simple thing. So it's based on this indentation. So how much they penetrating? And based on the penetration, you kind of introducing the spring that push them back. I mean, push the ball back where it came from. So that's the technique. And, you know, this is how much it is a penetration. And this spring coefficient is typically based on material parameters. So if you know that this is a steel, so then the stiffness, that is a function of this penetration. Penetration is the x here. This is my stiffness. Now, one of the important things in a modeling perspective is that if you have like a description like shown here, this would be your force, push them back. Now, if you have this x, the way I describe them here, you know, the force, if this is a force and this is an x, you know, if it is approaching the surface and if it is coming to the surface, it behaves like this. This angle here is going to be my stiffness, this guy. But you see that here there's discontinuity. And the simulation model, they had nothing more than discontinuities. Even this is not serious discontinuity, but there's still a discontinuity. And typically what you do is that you want to smooth out this discontinuity. The easiest, you are not saying that this x is as it is here, but you put the power here, x power 1.5 or x power 2, it becomes to be smooth. That's the simple way to avoid that. Okay, so this is a smooth dynamics based on this. This is an equation. Like what I just put it in a writing in a previous slide. So no difference here. N here, which is this exponent here, typically is not 0. It can go all the way up to the 3, depends on your application. But most commonly is like 2 or 1.5. So make sure that this, when you hit this ground, is a smooth. All right. Now, you guys know there's all right, this is pretty much how it behaves. But you guys know there's a fantastic professor, Jussi Sopanen. You all know him. Some of you guys know him. Okay, anyway, so he's a fantastic professor. When he was younger and when I was younger, we made a paper about how to model the ball bearing. Ball bearing. Well, this actually can be used other bearing types too, but ball bearings. And this was based on the penalty forces. So it was a pretty simple idea. So we look at the penetration of each of the balls for the inner and outer ring. And based on how much there is an indentation, how much there is a penetration, they will be pushed back. And this is the way to model the bearing. It's like penalty force based method. Simple technique, and it works pretty well. What happened to this guy? It's here. Okay, so with this technique, you see that, you know, here the balls in lower part of the system is only contacted and upper parts are not contacted at all. And here, how come it's doing something like this? I want to take, okay, I know why. I better not to touch, I said that I better not to touch this part, and I better not to. Okay, so this is how this is based on. Look at this equation. Of course, this is a complicated because, the stiffness here is based on the geometry and material, so it's not that easy to describe, but it's the same thing like I just described. And the end here is a 1.5. This is how much there is a penetration, this is a stiffness, and that's it. And then you compute the forces for each one of the balls in each of the directions and moments too. And you're good to go. That's all you need. And then there is even the software that you can put these parameters in advance, and when you do that, then this is how the model works. You see that this reaction force is fluctuating all the time. And it is fluctuating because, in a bearing, what can happen is that, there could be a configuration like this, where the force here was pushed downwards, so the reaction force traveled to these balls like this. It could be another scenario that is like this. The force traveled directly to one ball. And that's what the fluctuation all the time. So is it coming with the two balls or one ball? Is even introducing a little bit of changes. What is this? Yeah, I think we saw this already. You can introduce a little bit of defect like oval inner ring. So this is what's going to happen as a consequence of that. There's a crack that is traveling, and the crack is hitting that you see when the reaction force is bouncing back and forth. And like this. Okay, that was a penalty paste. Jussi is making fun of me because when we did this paper about the bearing modeling, this was more than 20 years ago. This was roughly at the time that you were born. So it was published 2003, published. And I guess that's your age too, roughly, that age. Okay, so Jussi is making fun of me because when we published that, I left this bearing modeling pretty much soon after that and haven't really touched that. Whereas Jussi have stayed in this bearing and rotor dynamics all the time. And of course, he's very strong in this field. So he's making fun of me that, this paper, this bearing paper, surprisingly enough, is the most cited paper for Jussi's career in my career, the one that we saw. And he's like, my knowledge about bearings is non-existent, but look at your publication. The most cited paper in your career is still bearing modeling. All right, okay. Anyways, back to the penalty forces, because we have this cone complementary to cone. It's simple to use. It's straightforward to use. And it's not necessarily so easy to compute, because what can happen is that, you need to use a very dedicated time step. Again, if I take my ball and I'm going to drop my ball to this surface, if the ball is here, that's okay. But if in the next time step is this much penetrated, and if this is a steel material, both are steel material, the force you're going to generate is enormous in a size. And the ball will fly out of space. That's not happening in reality. That's not possible in reality. But that's why this system is, or this integration, this method is very sensitive for integration settings. It's a very often used method. It's called smooth dynamics because it's smooth all the time. And particularly when you use an X power other than a 1, even that is smoothed. So that's what it is. Now there are alternatives. There's a contact force can be described by penalty forces. Drawback associated with this method is damping is difficult to describe. Multiple contacts are difficult to describe. Method is sensitive for integration settings. Okay, so let me take myself back here. And then the last thing we're going to discuss is this method based on, hold on. Okay, how is the success rate? Role of mass invariance. But this is going to be very high, I think. Oh, 94. Not bad at all. Next one. Contact force can be described using penalty forces. Drawback associated with this method is damping. It's difficult to describe. Multiple contacts are difficult to describe. Method is sensitive to integration settings. And the one only is correct. Where that I am right now? I'm somewhere here. Put me back here. Here, this is where we are at. Okay, you guys think about this, and I'm gonna shortly explain this using cone complementary approach. Now, this is all about these inequalities, many of these inequalities, and you can treat them in a computationally efficient manner. So it basically cut the corners is like this. You need to know that how are the east of the surface, how they're traveling. And then you just say that you can travel the way you want, but no penetration. Absolutely no penetration. When there's no penetration, you can have a lot of these inequalities. You can treat them in a way that is computationally very efficient. Okay, here's an example. Here's the balls. They drop like this. Okay, this is less. I said that the limit is in 100. So yeah, it's actually, this one is more than that. I wanted my good friend Dan Necker to explain this to you. Let me see, I just need to make sure that you can hear the voice. And I hope that the online participants can hear the voice too. This is gonna be my last slide today. What is this? Huh. Oh, I think I just converted this to be, okay, let me see if I can find this easily from YouTube. This is this guy. Okay, let me make it bigger.
Good afternoon. My name is Dan Egroth. I'm an assistant professor at the University of Wisconsin in Madison, and I want to start by thanking you for taking the time to attend to my presentation here. I'm going to talk about this topic of taking the leap from multi-body dynamics to many-body dynamics. And let me first tell you what multi-body dynamics is. In general, multi-body dynamics looks, for instance, at the motion of this vehicle. In this case, this is a project that we have with the JPL, and you have a vehicle with a relatively small number of parts. What makes this a many-body problem is when you start looking at the granular terrain that the vehicle moves over. And in reality, what they're interested in, they want to see if this vehicle gets stuck in the sand. Now, in 1 cubic meter of sand, you have about 1.5 billion particles. And although you don't see this in this picture, in this movie, sorry, those small parts, they move. And you solve some equations of motion, and they come back to tell you at each time step that I don't move, I don't move, I don't move, I don't move. Once in a while, they move. But nonetheless, you have to solve at each time step a very large problem. Now, this is a simulation that is about probably 2 or 3 years old. And I showed it to some Army guys, and one of them raised his hand and he said, so why is that Mars rover moving over potatoes? Are there potatoes on Mars? And you know, this is my point. There are no potatoes on Mars, but you cannot go today to very small dimensions for granular material, because if you have, for instance, like a commercial off-the-shelf package, and you run a dynamics analysis, multi-body dynamics, classical multi-body dynamics analysis, with 32 balls dropping in that bucket, and you look at the time evolution of the system, it takes here for 32 balls about 600 seconds to understand the dynamics for 3 seconds. And not only that, but if you look at the shape of the curve, it's a quadratic function that describes this dependency, and a very quick back of the envelope computation tells you that if you have 1 million particles, it takes, for 3 seconds of simulation, about 25,000 years to run that analysis.
25,000 years.
With all this Medicare discussion and cuts, I'm not going to make it that far. So we need a different solution here. So this is the solution here. We change the math behind the formulation. And this is a system that has about 1 million parts, and they're moving, and we're tracing the motion of every single particle and how it collides with any other particle in the system. And there's like a ball of a lower density material, and it flows on that. So here is classical multi-body dynamics. I'm not going to get into details, but there was some math, okay, going from multi-body dynamics to many-body dynamics. And once you take care of this problem from a different mathematical formulation, all of a sudden it becomes feasible, okay? And when it becomes feasible, then the next thing that you want to ask is, well, how close do the results come with respect to reality? And here we have like a silos, like a flat Hopper simulation, and we ran that simulation, and then in the lab, we went and we took something similar. A graduate student, low salary, filled it up, painted the balls, and, we did that simulation, and then you put them side by side, and here is what you have, experiment and simulation. And they look pretty much the same. And we did some other simulation, but I'm not going to share the results here. Of course, if you look at this problem, you have millions and millions of bodies that move. Now, the beauty of it is that basically they all move the same. So there is a lot of scope for parallel computing in this. And this is where you can use, for instance, GPU computing or multi-core computing. And this is what we did. And we implemented, for instance, here you have a system that has about 500,000 parts. And this is a project that we work for the Army. And they're interested in how the terrain deforms on a track vehicle. And it took about, for 18 seconds of simulation, it took about 1 day to carry out this analysis. Now, you can go beyond that, and I have to tell you that, I grew up in a communist country, and it was like, food shortages and such. So one of my recurring dreams was like, eating lots of chocolate. And here is it, I can say that I'm a happy man. My dream came true. Either if it's like a virtual world, like, look, I have lots and lots of like chocolate here. Now, the tricky part about this is that it is a simulation that combines multi-domain, it's a multi-domain physics simulation. It solves at the same time the Navier-Stokes equations and the Newton-Euler, and it's done in a parallel fashion. And if I were to conclude, this discussion, it boils out to one idea. There is a lot of computational power today, like parallel computing and such. It takes new math that you can map on that parallel architecture, and wonderful things happen. And with this, I thank you again for taking the time to attend my talk.
Okay, so that was it. So he said many body, from multi-body to many body. Yeah, okay, enough. So he said from multi-body to many body. And the trick was to be able to use parallel computing, CPU and such, but they go up to the millions of particles. And they are, that of course, is you're still not able to model all the travel and how you have for example, the military vehicle goes top of the travel. That's still very, very difficult to do, particularly in real time, not possible. But anyway, so things are moving in this direction. So it's from multi-body to many-body. And it's about the contacts, how you describe the contacts. Other than that, everything else remains pretty much as they are. Okay, now, next week, like I said, please come, because this next week, hopefully going to change your career direction. It's going to be very impactful. It's going to, how you can tell the story if you go to interviews, how you can interview yourself, how you're going to make yourself as a trademark. That's what it is. And then week after that, please come back again. It's going to be me. Wrap these things up. I'm going to explain to you a little bit about how we can use flexible multi-body dynamics for stress analysis and fatigue life prediction. And then you're going to get all the questions needed to next exam. That's it. Thanks, guys. Appreciate your patience. And I know that it's not been easy, but everything going to be great. So the sun is shining and summer is coming, so enjoy your life. Okay, this is where I'm going to close my streaming today. We'll go and have a lunch. Thanks, guys. Oh, yeah, the last one. Last one. Okay, this one here, is it going to be 100%? No, it's going to be more. It's going to be, oh, it's the lowest today. Method is sensitive for integration settings. That's what it is. Thank you. All right, so I'm going to see you not next week, but the week after that.